Hello, everyone. Welcome to Coffee with Caleffi. Today, we are doing hydronic zoning from design to installation. So we've got our favorite engineer and favorite contractor on the line today to go through some tips from kind of the paper all the way through the execution of the system. So today, we're going to go through a couple housekeeping slides, and then I'm going to switch seats with our second presenter here. So if you're having issues with the audio, best thing to do is log out and log back in. If you hit yes in the presentation survey at the end, if you want a copy of a PDF of the presentation, I'll send that to you, and then we'll put this on YouTube as well. Okay, and then we can send, if you attend, we'll send you a certificate of attendance that maybe you can submit in your jurisdiction, depending on where you live, depending on what organization you're working with, but it'll have all the details of the class. Then this is the first screen grab I think we've shared. Hydronics 36 is in the final stages. We're just doing the last couple pages before we'll get that sent to the printer. So if you are on the call and you'd like to make sure that you're on the list, if you haven't received this in the past, you can go to that hydronics.caleffi.com. I'll put these links in the chat a little bit later as well once we get started, and sign up for Hydronics 36 so you get a notification when the digital copy is available, as well as can get a hard copy in the mail. And that's kind of similar to the topic today, all about zoning. Next month, we're going to have our tech support team. We're going to have Matt and Ryan talking about digital versus thermostatic mixing valves. So we make both of these. We get calls all the time about, what's the best fit for this application. We'll walk through the conversation to make sure you understand when you would lean one direction or the other. So the team will have some real examples from the phones. And then today, we have John Siegenthaler. Oh, sorry, we've got one more. So this one, I don't know if that is coming up dark or not, but I'm just going to explain what this is. So we have been focusing on a trade organization or something like that every month. I wanted to mention that the ASHRAE Presidential Initiative Challenge is open now. So there's a link that I'll share as well that you can join there. This is for the young engineers in ASHRAE, kind of subgroup of the ASHRAE membership, to submit cool projects. And it has to be something that you're actually going to put together with your firm. But you can get money back from ASHRAE. You can submit kind of like a grant type thing, but really cool projects, a lot of decarbonization projects and things like that from last year. That was kind of the name change that they went through this year. So just wanted to put that in front of everybody. If you have a young person in your staff that is a part of ASHRAE and part of the Young Engineers of ASHRAE group, this is a great way to get money back for cool ideas with your projects. And then with that, I think that takes us to our presenters today. So I'm going to switch seats with Bob Hot Rod Rohr, and John Siggy Siegenthaler is on the call here, and they'll take it away with the rest of the hydronic zoning slides.
Well, thanks, Max, and glad to be here, and also glad to be with my good friend Bob Hot Rod Rohr. We're going to tag team today. We're going to talk about several different types of zoning. And then Hot Rod's going to show you some different examples, some of the actual products from his lab and workshop out in Utah. So let's start off with kind of a definition. What is a zone? Well, it's any area of a building where the air temperature is regulated, typically by a thermostat, but it could be by some other type of temperature sensing control device, such as a non-electric thermostatic valve. And again, we're going to talk about both electric-based devices for zoning as well as non-electric devices. What are the benefits of zoning? Well, it allows occupants to remain comfortable, different areas of the building. It allows those occupants to have different comfort preferences based on activity levels, based on internal heat gain, maybe group preferences and so forth. So basically different temperatures in different areas of the building at different times. And when the device controlling the temperature is reduced in its setting, you can save energy by going to lower temperature settings. And that's really where zoning kind of got its start, is the idea that if you're not necessarily needing a normal comfort temperature like 70 degrees Fahrenheit, maybe it's a guest room, maybe it's a workshop area, something that's occasionally used, you can reduce the temperature and save some energy. And hydronic systems have used the concept of zoning for decades. And just an example, here's a system that drawing down there on the lower left actually goes back into the very early 1900s. You won't see a circulator in that system because circulators hadn't been used yet. Electric motors weren't around yet. That was what we often call a gravity system. The circulation was all done by the buoyancy differences between hot water, which is lighter than cool water. The pipes were sloped. But if you look carefully at some of these radiators, you're going to see a valve like this, some type of a manually adjusted valve that would just simply change the flow rate or allow the flow to be completely stopped going through an individual radiator. So that's, again, going back literally over a century. And of course, today we've got modern thermostats, whether they're Wi-Fi based or just digital thermostats. And those are controlling devices such as zone valves here or zone circulators. And again, we're going to talk about both of those. But we're also going to talk about devices that don't require electricity. And I drew a little box around that. This is a thermostatic radiator valve, and that's attached to a panel radiator. And that allows that radiator to adjust to changes in air temperature. For example, internal heat gains might push the temperature up. That valve will reduce the flow rate under that condition and maintain a fairly accurate, let's say plus or minus 1 degree Fahrenheit of set point. And again, we're going to get into that type of zoning as well. So what are planning considerations for zones? One of them is thermal mass. And I've got a couple examples here of a radiant slab, 4 inches of concrete, 6 inches of concrete, very high thermal mass. So it's going to have slow response characteristics. Think about turning an ocean liner with an oar as an example. Eventually you could do it, but it's a very slow process. Versus a low thermal mass heat emitter like a fin tube baseboard or a panel radiator or a fan coil. They respond very quickly. And just it makes sense that you don't want to combine a high thermal mass heat emitter with a low thermal mass emitter on the same zones, because the low mass emitter is going to reach a temperature much faster than the high thermal mass. So in general, you want to separate those based on thermal mass. And here's just an example. This bar graph gives you kind of a relative comparison between the thermal mass of different emitters. And just to put everything on an even keel here, what I did is just determine how much of each heat emitter is necessary to provide 1,000 BTUs per hour at 110 degree average water temperature in a space that's at a 70 degree temperature. And I'm sure it doesn't surprise you, the 4-inch concrete slab is by far the highest thermal mass. And then we start to work down cast iron radiators, underfloor tube and plate floor heating. And then way over on the right, low mass panel radiators literally are less than 1% of the thermal mass of that 4-inch slab. Both high mass and low mass emitters, they both have pros and cons depending on the situation. But in general, the idea is don't mix them on the same zone. Here's another consideration. We call it interzone heat transfer. Just imagine that we've got a building envelope, and today energy codes require fairly high thermal resistance. So those two yellow walls I'm showing are 30. And then somewhere in between, we've got an uninsulated partition, and we have an open door between those two rooms. And the combination of the low thermal resistance of that partition, as well as just free air movement between those rooms through the open door, it's hard to maintain a significant temperature difference between those. And I'm showing 75 and 65. That would be very difficult to maintain. Even if we shut off the heat in the space at 75 degrees, we would find that it would eventually equalize very close to the other temperature and vice versa. And the higher the thermal resistance of that building envelope, the more difficult it is to just maintain significant temperature differences between these spaces. Now, if there's some reason where you really need to maintain significant temperature differences, you can insulate the partitions and basically keep the door closed, or possibly even use an insulated door. But most homes are not built that way. So again, consider interzone heat transfer and really kind of move away from the idea that I could keep bedroom number 1 at 65, I could keep bedroom number 2 at 75, and I can have an uninsulated partition between them, and both doors would be open. Internal heat gains. Anything that uses electricity inside the building envelope ultimately creates heat. It could be cooking, it could be the heat output from a refrigerator, lighting, microwaves, even a fan. If it uses electricity, ultimately that energy that goes into that fan ultimately ends up as heat. And of course, solar gains is another form of internal heat gain. And these internal heat gains can vary certainly from one room to another based on solar exposure, based on the appliances or the equipment that are in those rooms. So when you have a situation where you have the potential for widely varying internal heat gains, those are good spaces to consider on separate zones. And it could even be room by room zoning to allow each room to independently adjust the heat output from the hydronic system based on what is happening with internal heat gains. And I put down over here that at times internal heat gains can fully heat the building. Passive solar houses, it could be 0 degrees outside with a strong solar gain in through a significant glass area. There won't be any need for heat input. So that would be, again, a good space to consider as a separate zone. Okay, now we're going to talk first about zoning with circulators. And these are a couple graphics that will be in Hydronics 36. The first one here on the left, that's a very common residential system. We've got 3 zones of fin tube baseboard, each with their own circulator. And if you look carefully at the circulators, you see that little Z shape. That means there's an internal check valve. Having a check valve, whether it's internal to the circulator or external, extremely important. We're going to talk about it in more detail. Down at the bottom, we've got an indirect water sphere. Now, that's a conventional boiler that has low flow resistance. So if we had all 4 of these circulators on at the same time, we don't have much pressure drop through that heat source or through those headers. And you can see the note here, it says generously sized headers. That's important. We want to keep the pressure drop or the head loss through those headers very small, because what that gives us is a quality called hydraulic separation. Over on the right, we've got another 4-zone system. In this case, it's 3 zones of floor heating and an indirect water heater. You'll see there's a set 4 hydraulic separator that separates the headers and the zone circulators from the modulating condensing boiler on the left side, and it's got its own circulator. So this is providing the air and dirt separation. It also is providing magnetic particle separation. So if for whatever reason you have some iron oxide in the system, the magnet will capture that, and the magnet can be removed, and then the fluid that would have that in it can be flushed out the bottom. But what is it doing? It's actually separating the pressure dynamics of the boiler circulator from those of the distribution circulator. So we don't get interference between the circulators. Now, again, we'll be talking about that in more detail. So advantages. Failure of one circulator only affects one zone. So if one of the baseboard zones has a circulator failure, which can happen, but quite honestly, it's relatively rare in a well-designed, well-maintained system. But only that zone would be affected. And today, most of the zone circulators have multiple speed settings. So based on doing flow rate and head loss calculations and comparing those results to pump curves, you can reduce energy input to the system, electrical energy input, by adjusting the speed of the circulator. So those are a couple advantages. Disadvantages, and Hot Rod, I'll read these, but if you have any other comments, jump right in here. But real quick, you're definitely going to use more electrical power with zone circulators, especially the older permanent split capacitor motors that have been around now for several decades, compared to zoning with valves.
Yep.
Typically lower distribution efficiency compared to valve-based zoning, and that's simply how many watts are being used by the distribution system to deliver the heat on a design load condition. Um, and circulators tend to have actually lower distribution efficiency. And I put down here more subject to forward heat migration compared to valve-based systems, especially if that check valve, for any reason, gets a little bit of dirt in it, something that doesn't allow the disc in the valve or the flapper to fully seat. You do have more potential for forward heat migration. And Hot Rod, do you have any other thoughts on zoning with circulators?
Yeah, I mean, we're getting closer and closer to that day. I think you got some updated information on when you're only going to be able to get ECM circulators. That the old standard PSCs are kind of going away. Two things about that. Number one, they're going to be more expensive. They are more expensive, and it just takes more to make an electronic pump than a typical PSC type of pump. And then also knowing that that's going to happen, and if you're already using ECM circulators, that's why it's really critical that we want to have that magnetic separation component to our systems. Put it in now, even if you're using the old style circulators, knowing that those pumps are going to turn into your magnetic separator if you don't have one in the system. And that can be expensive. When you have one that seizes up like that and you send it back, that's not a warranty issue.
Yeah.
You're going to have to, get a new circulator if you jam them up with magnetite, and that's where it ends up, is inside those new, or can. I'm not going to say it always does, but Siggy talked about magnetic separations both in that hydro separator on the right and a separate component on the left there that has a magnetic function too.
Yeah, and that's getting critically important because we're seeing more and more ECM circulators come in. And keep in mind that some of the OEM circulators that are coming into modulating condensing boilers, and especially heat pumps, air to water heat pumps, those are ECM circulators. We don't want to pump magnetite into a brand new heat pump. We're going to foul up the heat exchanger and potentially have some problems with those internal circulators. So just a couple details. I mentioned it is important that you've got check valves, and just to show what happens if you don't have check valves in each circuit, here we've got a circulator that's on, and over on to its right when it's off. So normally we'd follow the flow up through the circulator through this zone, and it comes down to here. And we'd like to think that the water is intelligent, that it knows it's supposed to go back through the boiler, get reheated, come back up. And some of it will. But also some of it is going to go this way. It's going to flow through that circuit in reverse because there's nothing to prevent it. It's going to cool off to some degree, and then it's going to flow back, and it's actually going to mix with some of the hot water that has gone through the boiler. So that's doing two things, both of which are undesirable. One is you're reducing the supply temperature going to the zone that's active. It's not getting the full benefit of the temperature of the water coming from the heat source. And secondly, you're going to get some heat output. Even though the flow is in reverse, you're going to get some heat output in zones that don't need that heat. The thermostat isn't not calling for heat. So if you take this and just extend it to 3, 4, 5, however many zone circulators, the general idea is it's really simple. You need a check valve in each one of those. And there's a couple ways you can do it. Over here, we're showing the internal check valve. Most of the circulators that are sold today as zoning circulators, common ones, Taco 007, Grundfos 1558, so forth, they come with internal check valves that just slide into the volute. But Caleffi actually does make a nice serviceable, and that's a key word there, it's a serviceable check valve, meaning that you can open these unions up, and if something did get clogged or jammed into the mechanism in there, you could clean it out, put it back in. A couple things on that. I've got In general, when we're placing circulators in a system, we'd like to see a minimum of 10 diameters of straight pipe on the inlet of the circulator. It's simply to calm down turbulence that would occur, for example, here at a T in a header or through some component. And also we'd like to see some distance between the outlet of the circulator and the inlet of a check valve, so we don't get turbulent flow going directly into that check valve. And Hot Rod, I'm assuming over the years, you've probably seen some projects where you get rattling check valves.
Yeah, and that's, I think, the main cause of the failure of the check valves. They just rattle their brains out eventually. Now, if you can see behind me, I've got that clear glass pipe. I actually put a pump next to that with the check valve, and so I could look in there and actually see the check. And I actually put a video of that on Plumbing Perspectives site. It shows that check, just even a good air-free system, it shows that check just always chattering around. And as you change the pump speed, you can see the frequency of that little check vibrate. And it's not a great place to have a check right at the turbulent condition at the discharge of that circulator. So I would, suggest a check like we show separate at that distance away from the discharge of the circulator. Just keep the rattling away.
Yeah, and Hot Rod, another thing, and you taught me about this. One of the things that can happen when you have a circulator that is in a pipe with upward flow, as you're commissioning the system, if you get some air bubbles trapped down here in the impeller,
yeah,
it is possible that circulator can't clear itself, because that check valve does have a forward opening resistance, maybe about half a PSI. And what will end up happening is you'll get this mixture of air bubbles and water around the impeller, and the circulator simply can't, I'll use the term, it can't grab the water and clear itself of that air. Whereas if you put the check valve up here, those air bubbles can rise up out of that volute. And now the circulator will be able to grab the water and clear itself out. And so that's another advantage of using a separate check valve compared to just the internal check valves in the circulator. And then on the return side of these zone circuits, if the piping is small enough, and I believe companies like Webstone, as an example, build these purging valves, which is basically an inline ball valve with a side port hose bib on it. I believe they go up to 2-inch pipe size with that. If you're working with larger pipe sizes, it's probably going to be something like this, where you can close the inline valve, open up that valve. And the idea is during purging, the flow is going to go up through the circulator, out through the circuit, and then with this valve closed, it's going to exit. It's going to push the air ahead of the water, for the most part, and it's going to push it back out of that circuit and back into a purge card of some sort, or just to a drain. So that's a way to expedite air removal out of that circuit. So those are just a couple details when you're zoning. And by the way, if you're zoning with zone valves, I would still suggest these are good details on the return side of the system.
Those little valves with the side port like that with the hose connection are a good place to inject chemicals into the system too, because it is a ball valve with a hose cap, and Fernox and some of the other brands make an aerosol can that actually screws right onto that, and you can squirt some a conditioner or cleaner into your system. So it's a nice access port.
Yep, very good. And then, earlier we talked about hydraulic separation. And what is it? Well, anytime you have more than one circulator, if you have two or more circulators that can operate simultaneously, and that's certainly possible with zones, we don't want them interfering with each other. And the key concept to achieve hydraulic separation is to identify what we call the common piping. And in this case, it would be the supply header. In this case, it'd be a cast iron boiler and a return header. Those pipes are essentially common to all three circuits. Now, yeah, you can argue in here they're not necessarily all common, but these headers should be short. They should be generously sized. A good guideline is that with all the zones operating at their design flow rate, the inlet to the header should not exceed a flow velocity of 2 feet per second. That keeps that head loss very low. So when the head loss through the common piping is kept very low, you will achieve hydraulic separation. And there's several ways to do it. Cast iron boiler systems with zone circulators have always, assuming the headers have been kept short and generously sized. And honestly, I have seen systems where that was not true, where somebody put like 6 zones in and they used a 3/4 inch copper header for it. But in general, when you had these larger headers and short headers and a cast iron boiler, you had hydraulic separation just inherent to the geometry of the system. You can do it with closely spaced T's like this. Okay, so that if there's a circulator out here for a heat source, the closely spaced T's would isolate the pressure dynamics of the boiler circulator from the zone circulators. A buffer tank can provide it. And then finally, you've got, in this case, the SEP4 hydraulic separator, which gives you hydraulic separation, but it also gives you air, dirt, and magnetic particle removal. So this replaces the separate components for air separation and magnetic dirt separation. Any thoughts on this, Hot Rod?
No, I think it's a good showing the 4 different options there. People think primary, secondary with a continuous loop that goes around, is the only way to do it. But these are some good examples where, putting your loads in parallel instead of series makes a lot more sense if you're trying to get the same temperature to every one of those branches going off there.
Yep, the old days, I guess, for both of us, we remember when the primary secondary was really popular, and you would have pairs of closely spaced T's like this along a primary loop. And to your point, as you go downstream, assuming all these loads are operating, you're getting lower and lower supply temperatures to these downstream secondary circuits. Okay, so now we've talked about zoning with circulators. Let's switch over to motorized valves here. And these are basically the same 2 systems. All I've changed is the method of zone control. So we've got electric zone valves here. And in this case, I'm showing a variable speed pressure regulated circulator. We're going to talk about differential pressure control coming up here. Again, 3 zones of fin tube, 1 zone that is indirect water heater. We've got separate components for air separation, dirt, and magnetic particle separation here. Over here, we've got a modulating condensing boiler. It's generally going to have a higher flow resistance. So to create hydraulic separation between the boiler circulator and this variable speed circulator, the hydraulic separator will do that for you. So the geometry, if you compare this to the geometry of the systems with the zone circulators, you'll see they're very similar. Advantages, disadvantages. A single delta P variable speed circulator is ideal. That's what we've shown over here. These are widely available today from just about any company that is selling circulators for hydronics. Lower power consumption compared to zone circulators. Hydronics 36 will give you some specific numbers where we compare a wattage input to the distribution system for zone circulators versus that for zone valves. And because it's a valve that fully closes when it's off, it basically prevents heat migration. And for years, I've been a strong proponent of putting zone valves on supply side of the circuits. I know there are systems out there where they're on the return side. The advantage of putting them on the supply side is that they are a good blocking device for heat migration. And keep in mind that you can have 2-directional flow in a single pipe. If we were to remove this valve, hot water will actually go up through the center of that pipe. And then along the internal walls of the pipe, the heat transfer will cool that water, and you'll actually get a slight heat migration effect. I'm sure many of you have probably taken your hand and you keep feeling back away from the heat source. Why is this pipe warm? This zone hasn't been on for hours. It's because of heat migration. Some of it is due to conduction along the pipe, but a zone valve on the supply side, fully closed, is a good means to prevent that.
So answer me this question, Siggy. It comes up quite a bit. People say, well, if you put the zone valve on the return side of the piping, it has less pressure to close off against. Is that
not really, because as it's closing, as it finally hits its closed position, I mean, it's going to have about the same differential pressure.
Well, and the way I look at it, if you got 8 gallons a minute going into the loop, 8 gallons a minute's coming out the other end,
Yeah.
and it's still closing against that dimension of flow of water coming through there. They say, well, the pump's added the delta P to it. And so, at the beginning, you've got the delta P added to it that the zone valve sees when it's on the supply, where that gets used up or worn away as it goes through there. But again, you're just trying to close the door against that GPM flow that's the same.
That's right.
The GPM didn't go away at the end
correct.
of the loop.
And so the momentum of the flow, the mass times the velocity, the momentum of the flow is the same on the supply and the return side. Yeah, and so is the differential pressure drop across the valve because you have the same flow rate, whether it's on supply side or return side. So
yeah, it's a hard thing to visualize for some people. They think, well, the pressure gauge on the discharge of my pump is going up. I guess the zone valve is,
Mm-hmm.
But I think that good way to explain it, the momentum or the flow that's going through there is what you're trying to close the door off against with the zone valve.
Yeah, you literally can think of the water moving through the circuit as mechanical kinetic energy. The mass and the velocity is going to be the same all through the circuit, assuming the same pipe size. The mass flow rate's got to be the same, and the velocity, assuming same pipe size, would be the same too. So again, I tend to like them on the supply side because of their ability to minimize that heat migration effect into those zones. If you get a call, why is bedroom number 2 warm when I turn the thermostat down to 50? It might be due to heat migration because of lack of anything that stops that heat migration. And that actually brings up a point I should jump back to. If you're zoning with circulators, and that check valve we were talking about, it's important that check valve is a spring-loaded check valve, not a swing check. The swing check valves simply don't have the forward opening resistance to prevent flow from just heat migration, thermosiphoning flow. A spring-loaded check valve needs about a half a PSI to open. And some of you, I'm sure, remember the old, what were called flow control valves from companies like Bell and Gossett. I think Armstrong and Taco had them as well. They used a weighted plug as the deterrent against gravity or buoyancy-driven flow. So that check valve today is going to be a spring-loaded. And that is the type of mechanism that is in the internal check valves in the circulators. It's also the mechanism that's used in the Caleffi serviceable check valve. One of the things you see here in the lower left, it says requires differential pressure control to avoid excessive flow velocity. If we have a fixed speed circulator, every time we close a zone down, the differential pressure increases across the zones that are still open. And with 3 or 4 zones, you don't tend to feel too much of that. But when you have a lot of zones going and only, let's say you had a 10-zone system and only 1 zone is open and it's a fixed speed circulator, now you're going to get into potential velocity problems. We're going to talk about it, but since we talked about circulator zoning as well as valve-based zoning, and one of the things that I know Hot Rod and I, we've heard this question for years, so we want to get your opinion on it. In your role, do you prefer circulators or valves for hydronic zoning? And I think Max is going to run that poll and give us some results. So put down your choice here.
Yeah, and I don't think there will ever be an exact answer to that. I mean, sometimes it's personal preference. I mean, sometimes it just, you got to look at a lot of different requirements of that system to make that good decision. I mean, when I see a circuit where it's a kitchen circuit that's got 15,000 BTU load on it, it's got its own pump. I mean, really, where's that pump operating on its curve? Probably right off the bottom of the curve, trying to move 1 GPM through a circuit with even the smallest circulator money can buy. Really. Yeah. Wasn't intended to, run down at that lowest speed. Now they're getting better with the electronic pumps and stuff, but it just doesn't make a lot of sense to me to move such a small load with a dedicated circulator.
Sure.
But
sure, and I found over the years too, just to your point, personal preferences. I've met contractors, they won't, they do everything with zone valves. I've met contractors, they do everything with zone circulators. Honestly, I'd have to say it's probably almost a 50-50.
I would agree with that. And I've seen guys go one way and the other, then they go back to the previous choice. You know, they zoned out with circulators always, then they tried zone valves for a while. And now with these new ECM pumps that can do so much more controllability with them, you know, now they're going back to pumps. But we
Yeah,
think obviously zone valve is a better way. But
we were talking the other day, Hot Rod, about in some states there are incentives for ECM
yeah,
circulators, and the circulators after the incentive are almost free. They're very,
yeah,
very low cost. So that kind of skews the market a little bit in the sense that why would you pay X dollars for a zone valve
right.
when you have a subsidized circulator and you're getting it for $10, let's say.
Yeah, you still have to buy the isolation valves, but I guess that's a cheaper option than a zone valve. But
Well,
yeah,
that's a good point too. The isolation flanges. I don't know what's a set of 1-inch isolation flanges up
I
to today. Maybe $40,
I would say
$45.
40. I would guess $40, depending on how nice a
Yeah.
quality you want.
Yep. So that
So,
adds some cost in there.
yeah.
Um,
All right. What do we? Let's see if we got.
So it doesn't look like the poll launched for some reason. So what I'll do is put that poll in the post-webinar survey.
Oh,
But we
okay.
do have the second poll.
okay.
Looks like it did load correctly, so we can do that one a little
All
bit
right.
later.
We'll keep going then.
Okay. Keep going. Differential pressure control. As I mentioned, if we take this system, we've got 5 zone valves up here, and we've got a fixed speed pump. And this was very, common before ECM circulators. Most of the circulators that would be driving flow in a hydronic system were fixed speed. Now, they might have had speed settings, but at any given setting, the circulator just remains at a fixed speed. So if we look at it down here, what's happening when we have all those zones open, we have our shallowest head loss curve, and where that head loss curve intersects this green pump curve, that's our operating point. So in this case, we'd have a flow rate of maybe, I'm going to say about 10.5 GPM, and we have a relatively low differential pressure across the circulator. Well, as we start to close down the zones, so this would be 4 zones open, 3 zones open, 2, and then finally only 1 zone. You see how these system head loss curves are getting steeper. And what that implies is that you're getting higher and higher differential pressure across the circulator. And it also means that the zones that are active are seeing higher and higher flow velocity. And we've been in projects where we could literally hear the noise through a zone valve outside a mechanical room with the mechanical room door shut. It was just buzzing or singing away. And obviously you don't want that. So one of the classical methods that dates back again several decades to compensate for that is to put in what's called a differential pressure bypass valve. And this is a valve that it has a spring-loaded disc, and it simply opens at a certain setting pressure. And if we look at it on a graph, instead of this operating point moving all the way up this pump curve as the zones close, it's going to come up to what's called the threshold setting of the differential pressure valve. And it is as if the upper portion of that pump curve gets truncated to this black line. In other words, our pressure is going up from this point to this point, but once that differential pressure valve is active, we have very, very little increase in differential pressure. So that was a way to approximate what I'll call constant differential pressure control. It was acceptable and it worked, but today with variable speed circulators, that many of which have what's called a constant delta P or constant head setting, the way that's going to work is, let's start with these 2 gray curves here. The lower curve here, this is a system curve with 4 zones on, and the gray curve that I'm pointing the cursor at, that's the pump curve. So we've got an operating point here at about, say, 11 gallons per minute. Well, let's say we close a zone down, and it could be any valve-based zone. It could be an electric zone valve. It could be a thermostatic valve, anything that closes the flow off. Initially, the operating point is going to try to climb from A up to this point here. But the internal electronics in a variable speed pressure regulated circulator are going to sense that deviation from a constant differential pressure setting. In other words, they're going to feel the increase in differential pressure, and they're going to compensate by reducing motor speed. And when that happens, you can see this operating point eventually, within a few seconds, will settle down right here at point B. So the net effect is we've moved from A to B. We've reduced the flow rate in the system or going through the circulator because one of the zones is closed, but we haven't changed the differential pressure, which means the flow velocity in the zone circuits that remain on stays the same. So that eliminates that noise issue. In extreme cases, it would eliminate erosion, corrosion in a copper elbow, that type of thing. So that has become a modern, in a sense, replacement for a differential pressure control. Again, if you're dealing with a fixed speed circulator and zone valves, two things. Put in a differential bypass valve, first of all, and then you also want to select a circulator with a relatively flat pump curve. What you don't want to do is put a circulator with a steep pump curve. That's going to just exacerbate the change in differential pressure as the zone valves open and close.
And we still offer that valve, by the way, a differential bypass valve. It's got the PSI settings on it. And I mean, simply just a valve, you can see just a spring and a disc in there that opens up. I'm trying to do that. So if you come across a system like that has problems and you don't want to change out a pump, we can still sell you a differential bypass valve.
So we're going to switch. We're going to look at zone valves, and I know Hot Rod has got some valves to show you here. But real quick, the internals, you've got a motor and a gear train, and it basically rotates the shaft. The shaft's connected to a paddle, and the paddle either blocks the flow or opens the flow. This particular one also has an end switch, which is a little switch that closes when the valve is fully open. That can be used to signal other control devices in the system that the zone valve is open. And typically it's used to signal to turn the circulator on and to turn the heat source on. The newer valves coming from Caleffi are using posi-stop connections. That's an O-ring that provides the seal there rather than a wafer. And different union tailpieces can be threaded onto that valve. But I know Hot Rod has got some valves. Oftentimes we think, zone valves, if I'm dealing with a 3/4 inch copper pipe, I want a 3/4 inch zone valve, and that's as far as the thinking goes. But internally, these valves have different orifices, and they can range from a relatively small hole up to a much larger hole that the flow is going to pass through. And that's going to affect the pressure drop through the valve. And I can't say it right now, but Hot Rod, can you hold up one of those valves and just show kind of the differences in that?
Well, there's a zone valve with a 1 CV. It's a 3/4 inch zone valve, or actually it's a 1/2 inch, sorry, zone valve. And you can see the size of the orifice of the opening in that. And here's an example of a 7.5. So let's get them both side by side so you can see the difference there. So the question comes, well, why would I want a valve with such a tiny hole in it? And you can talk to why we make this valve and who would use that valve. Excuse me, probably not a valve you're going to find at your wholesaler typically. That's going to be an OEM valve that somebody, a manufacturer specified that specific valve. But what's the reason for the small hole, Siggy?
Well, you see this chart down at the bottom. Basically, it's a trade-off. The smaller the CV rating, the higher the close-off pressure rating. So close-off pressure is the maximum pressure that the valve can close against. And it stands to reason that that spring in that assembly inside the zone valve, it can only create so much force or torque on the shaft. So as the size of the orifice that the flow goes through increases, pressure times area equals force. So as that orifice gets larger, and you can see here the CV rating goes up, which means you have less pressure drop through the valve, but the trade-off is it's going to have reduced close-off pressure. Now, again, you can design the system so that a 20 PSI close-off pressure is fine. But you just have to make sure that you're not creating a circuit that has really high differential pressure when it's operating. Upsize the piping, use components that have lower head loss characteristics. But the trade-off is close-off pressure versus CV versus the pressure drop through the valve. Okay, real quick, electrically, there are three types of zone valves on the market. Caleffi basically makes a 2-wire or 4-wire version. The 3-wire version was around. I think you can still buy these probably as replacements. The 3-wire valve, the end switch is one side of the end switch is wired to the wire that also operates the motor in the valve. So that can be used in some circumstances. Certainly, if it's a 3-wire zone valve, you can replace it with a 3-wire. I like 4-wire because now you have an isolated end switch. That end switch can go to a completely separate circuit operated by a separate transformer. You don't have to deal with a single transformer. If you simply don't need end switches, you can order a 2-wire zone valve. And then Caleffi also makes the zone relay panels here for both zone valves as well as zone circulators. And it makes the wiring easy. Again, these will be in Hydronics 36, but basically the thermostats wire in across the top. The zone valves wire in across the bottom. You can wire the end switches in. System pump is on here. There's other circulator options depending on how the system is configured. But these are commonly used today to simplify the wiring when you're working with a multi-zone system. Another option that Caleffi has is what I call a power open, power close motorized zone valve. This is a ball valve rather than a paddle, but it doesn't have a spring in it. So you have to power it open, and I believe it takes about 40 seconds to open. And you also have to power it closed. And the circuitry is shown over here. Basically, these are switch or relay contacts. When you want the valve to open, you put 24 volts between the blue wire, and the black wire, and that will motor the valve open. And once that motor, or I should say, once the shaft, the ball is fully open, the unique thing about this valve is it does not continue to draw power. So yeah, it draws about 4 watts of power when it's actually motoring the shaft open, but when it gets to the end, that power requirement goes to 0. So that valve can sit there for hours in the open position, not drawing power. And in some applications, maybe off-grid applications, something like that's a nice feature. It also has a single pole double throw switch in it. So you have a normally closed as well as a normally open contact. You can use those to signal other control components in the system. Very high close-off pressure because instead of a spring closing that paddle, you've actually got a motor being driven electrically to close that ball. And ball valves are going to have a higher CV rating, meaning less pressure drop through that valve. And it is a slower cycling time, 40 seconds. So that would minimize any potential for water hammering effects in the system. So that is an option. It's probably not as common as the paddle valve in residential applications, but these are excellent valves in other applications where you need these features.
A couple applications that we see these requested for commonly is a pump and dump geosystem, where they need a high CV valve and they need a high shutoff pressure against that, whatever pump's pumping through that pump and dump system. And also some off-gridders kind of keyed into this and said, yeah, there's no parasitic energy when that valve is open. So for their battery banks and stuff like that, it's a little thing, but people that are into that, that's what they do, is try and squeak all that.
Yeah, absolutely.
Power consumption down as low as possible. So if you need a valve for either of those, we've got it.
Yep. Real quick too, and I'm going to keep moving. Thermoelectric valves. These are basically heat motors. They do operate on 24 volts. The features of them, they are completely silent. They are slower. Depending on the surrounding air temperature, they can take 2 to 3 minutes to open. You can open these valves manually simply by twisting the knob, the top of that actuator. And the same actuator fits either a valve body like what is shown here and in this photo, or it can be screwed onto a Caleffi manifold valve. So it's the same device, and it just allows you flexibility to either use an individual valve for one circuit or use a manifold. And again, these are available either as 2-wire or 4-wire. The 4-wire versions do have a end switch in it, so you can signal other components in the system.
And over the years, Siggy, we've designed this valve so it's a low power consumption. Now, in the past, you could only get 3 of them, maybe 4 of them on a 40 VA transformer. So it took a lot of power if you had, a bunch of like you see on the wall there. But now we've got them down to a much lower current draw. The trade-off, of course, it takes a little bit longer to open because you got less current going to heat up that wax in there. So a little bit slower, but you can get more of them on your relay box or on your transformer if you're wiring them up that way. So.
And you were telling me too, once they're fully open, that the inrush power, the actual motoring power drops considerably to what the standby power.
It takes a lot to get the wax heated up, but once they're warmed up, we've got a little graph of that. I don't know if we put it in here that shows how that power drops off once it's heated up and open. And one thing that you'll notice with this valve, if you've got them out in the cold garage, it's going to take a lot longer to heat up than if it's in your basement next to the boiler at 75 degrees, because again, you got to get the wax from whatever temperature it is up to where it can expand and open the valve.
Yeah, and it's probably not the best valve if you're going to put a valve right into like a baseboard enclosure or into the enclosure on a unit heater, where it's going to be surrounded by hot air. It's definitely going to take it's going to take longer to close in a situation like that. Okay, let's get away from electricity and go to thermostatic. Now, again, no power involved. We've got a valve body here that's got a spring-loaded linear shaft. This is not a rotating shaft. The spring holds the valve fully open. When you screw this operator on here, it's going to push that shaft down and close it. Here's a cutaway. And real quickly, there is a bellows assembly that has a fluid in it. And that fluid expands and contracts in response to the temperature around this portion of the operator. So as it warms up, it's actually going to push down on the valve shaft, and that's going to reduce the flow going through there, and vice versa. As the room cools off, that bellows is going to allow that shaft to come back up again. So features on it: it's completely silent, non-electric. And this distinct difference between this and a standard electric zone valve. This is a modulating valve. This is not just open and close. It can be in any position in between. One of the things that is characteristic of these types of valves from just about anybody that makes them, you'll see numbers like 1, 2, 3, and so forth on the actuator, not temperatures. And that's done for a number of reasons. One is you don't have to worry about the difference between a valve calibrated in Fahrenheit versus Celsius. And secondly, this encourages people to set the valve to a condition where they're comfortable in the room, not having to know what that temperature is. You don't have to know that it's either 68 or 70 or 72 degrees Fahrenheit to know if you're comfortable. So it encourages that. And just to give you an idea, here's what those markings on the actuator or the operator correspond to in temperatures in both Fahrenheit and Celsius over here. And a typical setting is about 3. You see the 3 is lined up here with the indicator. So that would correspond to roughly 68 degrees Fahrenheit. Simple, been around for decades, reliable. I really like non-electric thermostatic valves. They're what I call simple but elegant devices.
And very underutilized in the U.S. market. I mean, you go to Europe, you go into a castle that's 200 years old where they retrofitted panel radiators. You see thermostatic valves, and they just use them everywhere for every. It just makes sense that a non-electric, proportional zoning device. It doesn't get any better than that, because that's the thing in a castle. How do you get wires to all these different rooms? You just put a TRV on there.
Yep, and we've used these in heat pump systems. We've used them in biomass systems. They're not just for older systems. These can be very contemporary, are used in very contemporary systems. Here's a quick example. This is another flavor of a thermostatic radiator valve, or TRV. Here we've got a panel radiator. This particular one is a Myson product. You'll see at the bottom here, supply and return tube. But up in the upper corner, you actually have a valve assembly built right into the radiator. So there's a core assembly that screws into the radiator, and here's that linear shaft, spring-loaded. If you screw one of these operators on here, you've now made it into a self-responding zone. Each radiator becomes a zone because this is a temperature control device. So one setup would be, again, using a variable speed pressure regulated circulator, going to a manifold. This is what we call a home run system. So you've got 1/2-inch tubing going off to each radiator. Caleffi makes a nice little dual ball valve isolation valve that can screw in there. And then here's the thermostatic operators on each radiator. So each radiator becomes a separate zone. And we did a system a couple of years ago in a project. We used 10 panel radiators, each of which had a thermostatic radiator valve. And the circulator at full speed that drove the entire house was 44 watts at full speed, and typically would operate 25 to 30 watts. So we had really high distribution efficiency, 10 zone system, room by room temperature control. So each room could respond to internal gains and so forth.
And the pump modulates with the valves. As the valves open, the pump speeds up. So it's like a cruise control on your heating system.
It is. And that's a very good analogy. That pump is just a cruise control for differential pressure. And then these valves are essentially cruise control for room temperature. You can also get thermostatic control valves that have a capillary tube and a wall knob. If somebody can't necessarily bend over, if you have a low profile heat emitter and this operator is 10 inches off the floor, some people just aren't able to bend over to operate that. So you can do this. This capillary tube is 2 meters long, so it's a little over 6 feet long. This is not a wire. I can't overemphasize that. And I say that because we've had projects where people have cut these with diagonal cutters and said, I'll just put it back together with a wire nut. That's actually a little tube, and the working fluid is moving through that tube between this little piston assembly here and this wall actuator. Over here, here's a manifold, variable speed, constant differential circulator. And you see we've got 1/2-inch PEX going out to each radiator. Each radiator's got a TRV on it. Each radiator's got a dual isolation valve. Then on this end, I purposely threw in a radiant panel circuit. It could be floor heating, wall heating, ceiling heating. And that's where we use this assembly right here. So the valve body is mounted somewhere where you can get access to it. You don't want to bury it in a wall and put it behind drywall. You want to have an access to it. And then the setting knob is on the wall. And then down here, this is what we call an extended manifold system. What we've got here, instead of running all this PEX, we ran copper tubing along the main girder of the house. This is just 3/4 inch copper. And then in the same joist cavity that would line up with each radiator, we just stubbed out with 1/2-inch copper, transitioned over, in this case, 1/2-inch PEX, aluminum PEX. And then these just run through those joist cavities and then pop up through the floor to the panel rads. Here's actually an example of the capillary tube. If you look really close in that photo, you could probably see that little, what looks to be a wire. And that goes off to a radiant floor circuit. These two go off the panel radiators. So as long as your panel radiators and your radiant panel circuits are basically sized for about the same water temperature, it's fine to combine these on the same system. Okay. And this is one that Hot Rod and I talked about. If you want to have constant circulation and zoning, you can do it with a 3-way zone valve. And I know Hot Rod's got one there. He's going to show you the pattern inside there.
Quite see it, but it's in the picture in the back there. Yeah,
So,
it's a great way to run a system, especially a big radiant slab where you want to maintain a nice consistent temperature. just let the pump run all the time, and that water's always moving. And especially if you have, like as I do, I don't know if you can see behind me, I got a lot of solar gain into my shop. So what happens with this constant circulation in the winter, as the sun comes in through that glass, it warms the front half of my shop here, and now I'm moving that free passive energy around the building. So it's a simple thing to do with a three-way zone valve like that. So basically it's always running through the loops, and then when my thermostat calls for more heat, it opens the zone valve, the end switch turns on the boiler, switches the circuit the other way, and now I'm pulling through the boiler. So
yeah, we love this application in highway garages where we've got large overhead doors or fire stations. And the reason we like it is typically you get those cold spots near those doors, either from air leaking under the door or just a lack of insulation, a thermal break between the inside slab, and the concrete ramp outside. And with constant circulation, you're basically grabbing BTUs that are in the core of the slab, farther inside the building, and you're relocating them near these doors. So it kind of evens out that floor temperature. And just a couple cautions. These valves are available. These are basically three-way zone valves. They go up to a CV rating of 7.5. So you could use these in systems where you have, I would say, up to maybe 8 gallons per minute, something like that. But when you get up into a big system, if you're trying to move 25, 30 gallons per minute, don't do it with this valve. The CV rating simply isn't high enough. You need a three-way ball valve. It's the same concept as shown here. It's just a valve body that has a higher CV rating. So in a commercial application, again, highway garages that are 12,000 square feet with maybe 2 or 3 zones in it, these valves, the CV isn't quite large enough, but residential applications or light commercial applications, as long as you respect the CV ratings on these valves, you'll be fine. Okay. No, Max, let's run this. We talked about the differential pressure bypass valve, and we talked about it as kind of the classic way to control differential pressure in a zone valve system. But now with the new circulators, variable speed, pressure regulated circulators in the market, we're interested in your opinion on this. Again, in different roles, you may be an installer, an engineer, wholesaler. What do you see as the future market for these differential pressure bypass valves? Do you think their use is going to go up? Do you think it stay the same or decrease, or you're just not sure? We just want to get your thoughts on this valve as far as where you see it being used now and going forward.
And Siggy and I talked a little bit about with heat pumps, how there might be a new market for a valve like this where the heat pumps, what's happening with some of these heat pumps is the pump starts up before there's flow going through the system. So now you need a bypass or an escape route for that flow. So some people are building it into the systems, you said, Enertech or something.
They are. In fact, we have a schematic coming up here if we have time for it. If we don't have time, it's going to be in Hydronics number 36, where these differential bypass valves are actually being used. So a heat pump can recirculate the flow until the temperature of the flow comes up to some preset value, and then a valve would open and the differential bypass valve would close. So that is a very different application from what I'm showing on the schematic, but it is definitely a current and likely a future application. So Max, do we get any results yet on this?
We did. So we got 46% say decreasing, 12% said remain the same, and 26% said increasing.
Okay.
Increasing is good for business.
Okay. Now, I'm looking at the clock, and we're a little bit over here. I'm just going to very quickly go through these schematics. I don't really want to take a lot of time on them, but these are all in Hydronics 36 that'll be coming out in the near future here this fall. And they're all examples of zoning. So we've got a basic system with a ModCon boiler, zone valves doing space heating. We've got a zone valve doing an indirect water heater. We're using the SEP4 to isolate the flow dynamics of the variable speed pump from the boiler. So really simple, very common system. We're using one of the Caleffi zone control boards here to manage the wiring. So all the thermostats and all the zone valves and even the circulator wire back, and also the boiler. This is kind of the hub of the control system. So that's a basic system. Here's one with a split system air to water heat pump. It's doing basically it's using a tank here that's a reverse indirect, where we're heating the fluid in the shell of the tank. We have copper coils inside. That's for heating domestic hot water. And we're also using the shell as a buffering volume for space heating. Space heating's panel rads with TRVs, variable speed circulator. We also have cooling going on with a single chill water air handler. And here's an example of where those two motorized ball valves are being used. And here's a differential pressure bypass valve. Now, this is that new application we talked about. And the idea is that when this heat pump first starts up, gets a call for heat, the circulator turns on and it runs for about 2 minutes before the compressor starts. What we don't want to do is break up the stratification in this tank. If we just circulate this fluid, but without putting heat in it, we're going to break up this temperature stratification. So instead of doing that, both of these valves would be closed and the flow will simply go through the differential bypass valve, up through the separator, and then right back into the heat pump. So think of that as kind of a holding pattern until the temperature comes up. And once it comes up to the temperature equal to or slightly above the tank temperature, we open this valve and the flow goes right over there. Same thing for cooling. So that's one. Another system, 2 zones, a high temperature fin tube, 2 zones of low temperature radiant panel heating, an indirect water heater. We've got a discal dirt mag. This is a combination of air separation and dirt and magnetic particle separation. We've also got, let's see, a motorized mixing valve that is controlling the water temperature to these lower temperature zones. So again, we're zoning with circulators in that case. This is actually a system from a house I helped build for my daughter. It's using a lot of different zoning techniques in here. We've got a zone valve that controls flow to a manifold. That manifold serves a combination of some floor circuits as well as some panel rads. Notice there's no TRV on these panel rads. Okay, so basically a thermostat opens this, turns on the circulator, and this is all controlled as a single zone. This is all one big open area. Over here, we do have thermostatic radiator valves on this. We've got a towel warmer with a capillary tube TRV. We've got another floor circuit with a TRV on it. And so these are all independently controlled non-electric zoning. And here's what it looks like. We've left some extra connections on the manifold. So if somebody wants to add a towel warmer later on in another bathroom, for example, it's an easy add-on. The system basically uses the air to water heat pump to maintain this tank temperature, and it's got an electric boiler as an auxiliary and supplemental heat source. So a pretty contemporary system. And one thing I will point out before leaving it, if you look at these, you notice that the circuits go up and the air vent always has to be up. This is called an inverted manifold. And when you order the manifold from Caleffi, you'll see in the catalog that a standard configuration is with these circuits pointing down, air vent up, but in the inverted manifold, the circuit point up and the air vent points up. And over there, there's the zone valve that controls the flow to that one manifold. And I think, yeah, one more, and we'll go to questions here. I put this one in here to show a couple other ideas. One is there's going to be times, especially if you're adding heat emitters to a system or you're weatherizing the system and you're allowing the system to go to lower water temperatures. If we have a conventional boiler, we don't want to cause sustained flue gas condensation. Caleffi has a valve. It's called a thermal protect valve. It's a thermostatic valve. And what this does is it blends hot water coming out of the boiler with cool water to get a temperature returning to the boiler that is high enough to prevent flue gas condensation. Typically, that should be about 130 degrees. And these valves are available with different settings, but that's one detail. Another detail This is an external heat exchanger for domestic water heating. Basically, what happens here is when you draw hot water at a fixture, of course, cold water has to come in to replace it. It will trip a flow switch at about 0.7 of a gallon per minute flow, and then through a relay, and we've actually done this right through one of these Caleffi relay centers. It's just a relay just isolates the low voltage circuit from the flow switch to the line voltage to run the circulator. Basically, this is going to drive flow through the primary side of that stainless steel heat exchanger and put it right back in a tank. And the cold domestic water gets a single pass through that heat exchanger, and it can be fully warm. So if the heat exchanger sized correctly, it's basically an on-demand or an instantaneous way to heat the domestic hot water. This detail is used widely in Europe. We don't see it as much in North America at this point, but Hyrod, if I remember right, you built this into one of your systems back there in Missouri.
Yeah. The last house we lived in Missouri, I had that exact, well, I had a wood boiler connected in there too. So most of the time the tank was either a solar wood boiler. And yeah, I'll tell you, that hot water worked really well. Now I had a lot of buffer. I had a 500-gallon buffer tank, but yeah, I mean, it's as much water as you can run through that plate heat exchanger. If it's sized properly, it just hot water for weeks.
Yeah, and quite honestly, this is very similar to what combi boilers use today. They route hot water from, space heating water, I'll call it, through a brace plate heat exchanger using a flow switch to basically set up a valve that creates that flow. So, it's a detail I wanted to show just to get you thinking about when you have a standard buffer tank and somebody says, I need domestic hot water. You don't always have to use an indirect water heater to do that. This actually gives you the advantage that heat exchanger being external to the tank. You see there's a couple valves here on the domestic side. These are just these are purge valves. We can close the two inline ball valves and we could actually pump a mild acid solution through that side of the heat exchanger. If we have any scaling, we can reduce that. And there's actually products on the market, both the chemical and the little submersible pump in a 5-gallon pail, basically, to clean that heat exchanger. Worst case, if you really scale it up, you can replace it. With an indirect, if you scale up the coil, you have to put a new tank in. There's no access to cleaning that coil or replacing that coil. So it's again another little detail worked in with some zone valves over here. We talked about the purging valves on the return and so forth. So with that, Max, I'm going to turn it back over to you to close us out. And if we do have anybody hanging around, we could still take some questions.
And actually, the polls are working now. So I launched that other poll for the preference for circulators or valves. So I'll leave that open for a second. And then the last couple things here. So we'll be back again next month with Matt and Ryan for the thermostatic versus digital. One of the questions, John, you covered it, but I wanted to just double check. At the very beginning, you were talking about the short fat headers for piping configurations that you mentioned. The number that you said for sizing that, the question was, can you go up one pipe size? And I said, well, it depends. And the number that you gave was 2 feet per second,
right,
as if you're calculating for all of the zones to be on. So if you have like 10 3/4 zones going off of that, 1 inch wouldn't be
correct
in that scenario. So
so what you want to do is look at total GPM of all your zones and go to there's graphs, there's equations. You can do a basic calculation. If you know the flow rate for a given size pipe, you can figure out the flow velocity, and you try to keep that header at no more than 2 feet per second flow velocity. And where that number comes from, that's enough to entrain air bubbles and move them along. So if you have some air, let's say you had a vertical header for some reason and the flow was going down, you could still entrain some air and get it pulled through the system back to the air separator, but it's creating minimal head loss for you. And it's kind of interesting in Europe, years ago, looking at some of those first systems over there, you would notice that as a pipe came into a header, the headers would be noticeably larger in diameter than the pipe supplying them. And I always kind of wondered, why did they do that? Well, they do it to minimize any differential pressure or pressure drop along the length of the header. So essentially, all the zones are going to feel the same pressure at the supply as well as at the return. And with a variable speed pump in there, again, you're improving the hydraulic separation characteristics of the system. So I usually just throw out this idea, build short, fat headers and use the 2 foot per second criteria as a way to judge what that pipe size is.
Okay, perfect. And then I closed the poll. So in your role, do you prefer circulators or valves for zoning? We had 31% say depends on the project, which I think is fair, kind of how we've advertised it there. 27% steady preference for valves, 16% slight preference for valves, and then 13% each steady preference and slight preference for circulators. So probably what we expected, I guess, from a valve manufacturer audience. But I think that the 31% depends on the project is probably the key takeaway here, that some version of 1 ECM circulator or 5 mixed with 5 or 10 zone valves might be a great fit depending on the project. So
it's probably worth mentioning too that there was a European circulator manufacturer that at one point was creating what we'll call micro circulators. And Hot Rod, I'm sure you remember those. These are tiny little circulators that drew like 2 or 3 watts when they operated. And they were actually setting up for panel radiator systems. And the goal was to displace thermostatic radiator valves with these micro circulators. And the concept was sound. The cost became kind of prohibitive. I don't think it really ever caught on. But it was amazing to see these tiny little circulators that, as they say, literally maybe 3 or 4 watts when they're operating, and each one would operate as a separate zone. And, of course, it had to be wired and so forth. But, there definitely are applications where valves make sense. If you're only zoning at 1 or 2 gallons per minute, you really don't need a separate circulator to do that. That's kind of, I'd say that is definitely overkill. But if your zone needs 10 GPM or 20 GPM, it's a big commercial project, the circulator probably makes more sense. And again, you have to weigh out the cost options. With the circulator, you are going to have to put the isolation flanges in there. And when you get up into large circulators, that can add significant cost beyond just the circulator. Also, think about this. All the circulators require line voltage wiring. The valves typically are 24 volts. So in some jurisdictions, licensed electricians are required to do any line voltage wiring, whereas 24 volt wiring typically, that doesn't necessarily require a licensed electrician. So those are other factors that would weigh in on that choice.
One of the questions was about the radiator valves. Like, what is the life of one of these valves? And as a manufacturer, it's hard to put a life on anything because the system conditions are maybe 99% of the factor there. Have either of you ever seen like a wax element fail in one of these valves? Like, have you ever seen one of these go bad that like they stopped working outside of an obstruction or some sort of water quality thing? Like, is there a more stable technology that you can think of for a hydronic system than the wax actuator in a radiator valve?
I have not seen one go bad. I don't. Hot Rod, what are your thoughts on that?
Did you hear that, Don? Have you ever seen one of the wax actuators actually go bad in a thermostatic radiator valve? Like
I think that
mechanism of it,
the bellows in there could be damaged somehow, but
from a water quality issue, or just that the wax?
Yeah, I think it just leaks. The fluid of the wax in there could leak out over time, but I think they're as dependable as anything, certainly more than an electric motor.
Yeah, I really like thermostatic radiator valves combined with variable speed circulators. I use the term simple but elegant. No apps, No passwords, no wires, no batteries, just simple. And my experience has been excellent with these, that they've operated well. I've not known of any failures, but again, I don't check back necessarily with a project that's 25 years old to see if something like that's happened.
Well, I think that takes us through the questions that I was keeping an eye on that I wasn't able to answer as we were going. If there's something else I missed, I'll get back to someone after the webinar. That's all I have today. So thank you to the two of you for a great practical and design spin on this topic that we've talked about a bunch of different times. Thank you everyone for attending, and we'll see you next month.
Bye-bye.
Thanks, guys.
Thanks, John.